Hello everyone and welcome to Mass Analytics Masterclasses, where we'll be sharing with you useful tips when it comes to running your marketing mix modeling end to end. In the previous course, we have covered modeling, regression, model selection, ROI, and contribution calculation. In today's course, we will cover 3 of the most important techniques when it comes to run contemporary marketing mix models. The first one is pool regression, the second one is log linear, and the third one is nested models. Now, reflecting on the marketing mix modeling workflow, we are now at step number 4, where actually we are starting to model the data that we have. And that's where you need to take a decision on which algorithm you will be using. Are you going to use standard regression, linear regression, or are you going to opt for a pooled regression or a nested models or a log linear? In Master, you would be able to perform your pooled regression, your nested models, and your log linear in the module model. And actually, you can also concatenate some of those methods. For example, you can run a pooled regression while applying a log linear transformation and at the same time nest some of your models in order to obtain nested models. Log linear modeling. Let's consider the following model where we are modeling actually the sales of the ice cream, and we have 3 variables that influence the sales of the ice cream: distribution, price, and temperature. So what happens when price is equal to 0? In real life, you expect that your sales will be infinite. However, looking at this equation, if we replace the variable that is related to price by 0, we will end up with a finite amount of sale. This is actually counterintuitive. Distribution. What happens if your product is not at all distributed, where ice cream is not available anywhere? You would expect that your sales will fall into 0. This is actually not the case in this equation, because if you replace distribution by 0 in this equation, actually you still have some kind of sales. What happens if temperature decreases a lot? Your sales will become negative. So what happens is that this equation doesn't really help me understand and model how consumers behave in real life. And that's where actually linear models fail. To remedy the problems we have described earlier on, we use log linear. Log linear is actually a multiplicative model that is composed of 2 main categories of variables: the relative variables and the incremental variables. For example, distribution and price are considered relative variables. Promotions, TV, media, etc., are considered incremental variables. In this equation, what happens when distribution is equal to 0? Your sales will equal to 0. That's actually what we are expecting in real life. Now, what happens if your price is equal to 0? Your sales will be infinite. That's again what is expected in real life. In other terms, log linear is capable of better mimicking or translating the reality that we have seen earlier on in the ice cream sales. And that's why modeling using log linear is preferred to modeling using just simple and additive functional forms. So how are log linear models estimated? As we mentioned earlier on, the log linear is a multiplicative function, and we need to estimate the coefficients in order to report on the impact of the different factors, be it relative or incremental. In order to solve this equation, we need to apply log to both sides of the equation, and then we apply OLS in order to estimate the coefficients, as we do in standard normal additive models. How do we interpret coefficients in the context of log linear? If you are dealing with a relative variable, like for example price and distribution, actually the coefficient just depicts your elasticity, which is really nice to have. So by looking at the coefficient of your log linear equation, you are actually reading your elasticity. In the context of incremental variable, the coefficient depicts the percentage change in your dependent variable as a result of 1 unit change in your incremental variable, like for example television or display or search or even promotion. One of the challenges of log linear is that actually the business is expecting us to report on the contribution of each media and marketing activity separately. However, the multiplicative form of the log linear makes this very difficult and challenging. That's why we need to go through an approximation to make sure that actually we show contribution as a summation out of a multiplicative form. Obviously, this is an approximation which will result into a decomposition error. That decomposition error will be added to the standard OLS error. And that's why any algorithm that claims to approximate contribution in the context of log linear needs to make sure that this decomposition error is as small as possible. So if you want to compare different algorithms when it comes to performance when solving for the summation of contribution in the context of log linear, make sure that your decomposition error is as small as possible. What we have managed to do at Mass Analytics is that we have created an algorithm that really minimizes that decomposition error, and we are also capable of depicting the size of the synergy between each pair of variables.